Swayam Prabha. Digital India. Educated India.
Today we will be talking about design of embankments on soft soil using geosynthetics. This is the 34th lecture in this series. We will have some introduction. What are the modes of failure of the embankment in soft soils? What do you mean by stability condition? I will give an example as well. We know that soft soils are characterized by poor shear strength, high compressibility and low permeability, and if you are able to use a reinforcement effect when you have a geosynthetics or a, you have different types of materials that we studied. When you have a geotextile or a geogrid or a geocell, they introduce a reinforcement function. Actually, it is also called pseudo confining pressure. We have seen that when you put a reinforcement in the reinforced soil, like if you apply pressure, there is some it is similar to like it does not strain much because there is some resistance because of the friction. So, that we call it a pseudo confinement. We have studied that in the using the concept of Mohr circle earlier. Like you apply load and it deforms vertically and horizontally, but if you place a reinforcement, it does not deform that much. That effect we try to equate it to horizontal stress, equivalent horizontal stress. That is what we studied. So, that can be even obtained by a geocell. Geocell is nothing but a 3-dimensional structure in which you just put some material and then you try to compress the circumferential action of the geocell prevents the movement, and that is called confinement effect. So, the reinforcement and confinement effect, if we can make use of in the soft soils, that is going to be very useful. It improves the stability of the embankment, then it permits a controlled construction over soft soils. In fact, what happens is that in many of the soft soil areas, you try to use this, the soil is so soft and you bring in some other material like sand, and then if you start constructing actually normally embankment has to be constructed with a good material like reasonably, say for example sand or whatever. So, if you start putting on the soft soil this embankment, there is always a loss of this embankment material, all that sometimes to the extent of even 20 to 30%. If you have a geotextile at the interface and then start constructing, that loss could be prevented, the mixing of soil and the sand could be prevented, and now one can properly account for how much exactly is the amount of sand used and what is the settlement in the clay, what is the effect of sand, and all that one can study. So, it permits controlled construction over soft soils and it ensures more uniform settlement of the embankment. Settlements cannot be completely eliminated because the soft soil has some settlements and you can only preempt the settlements, right. We have studied in the case of pre-consolidation or the prefabricated vertical drains and all that, we can accelerate the settlement, but at the same time we can make it more uniform. That is what is important here. Like if you place a geotextile or a geogrid, what it just because it is a flexible in nature, then because of this whole material load acting on the soil through this geogrid or a geotextile, the settlements are uniform because it just adjust in such a way that the settlements are uniform. That is very important for us because sometimes for example, you have a road on the embankment and it is a differential settlement that leads to cracks and all other problems. It is not the total settlement. So, if you have an embankment, highway embankment on a soft soil, and if it is some uniform settlement is there, it is okay, it is a little bit of it is not bad, but at the same time if you are able to prevent a differential settlement, it is very good. So, that can be possible by geogrids or geocells and all that. And of course, people have seen cost effective solutions, that is why lot of work is being done on these lines and people have done it extensively. Okay. So, what is that effect? We will see. Say for example, I will show you an example. How do you construct an embankment? This is a soft soil is here, and then you try to put this embankment material. You series of compact in layers of say for example half a meter, and you go on constructing, and you can't construct very fast because the rate of consolidation of the clay is very slow, very poor. The soil is very consolidation, the time soil is, the permeability is so low that it will not really respond to the rate of loading. If the rate of loading is faster, what happens, the consolidation can be still, rate of consolidation is still lower. What happens? It results in undrained conditions. When the undrained conditions prevail, what happens? Effective stress comes down. So, the rate of, that is the reason why, say for example, you are trying to construct a reinforced embankment. See, this is you start with time, you start constructing, you start loading, there is a possibility that if the undrained conditions prevail and effective stress is lower, right. So, the factor of safety will come down, and it can be, we say that if it is less than 1 and at the end of the construction it could be, so which means it is lower, right. It is less than 1 and then it is likely to fail. And after that, what happens, the consolidation is slow, but then effective stress slowly increases and you will have a higher factor of safety. So, our objective is to see that you should always construct the rate of construction in such a manner that this condition should not come in the field. Even in the construction of embankment and soft soils, we do that. We do it, we call it stage construction. This is one way of stage construction, in which you just put say 1 meter of sand and then wait for it. You have some instrumentation also for that. You measure pore pressures in the field. The moment you put this sort of embankment, you have settlement gauges, you have pore pressure sensors, all that all that one can install and then see exactly what is happening, and then you can even check. So, if the pore pressures are going to be very high, then in fact, I was just mentioning one equation, it is called Cu by P equation. Shear strength of the undrained shear strength of the soil is there, and then there is an effective stress also. Actually the Cu by P equal to 0.3, there is a simple equation. For example, it shows that it gives an idea that P is nothing but the extra stress that you have to put, the effective stress. So, how much is that effective stress you have to put on the soil? If you know the undrained shear strength is available in, that information is available. So, once you know that information, one can really slowly construct this embankment, but rate of construction is so slow, you can't wait, you would like to construct the embankment very fast, and if you want to do that, this condition is there. So, to avoid that, best is to place a reinforcement. If you place a reinforcement, what happens? It is the reinforcement that takes care of the embankment loading. So, you can see that if you have a reinforcement, it will take the load. That is a beauty, like all the surcharge load, whatever you are getting from this embankment construction, it does not allow all the load to go to the soft soil. We see that it only that is taken care of by the embankment, the reinforcement here. So, that is what is the purpose of the reinforcement, or even confining action can be here, we will see that. So, what are the applications? There are too many here. Actually, wherever there are soft soils, it is well established, and you have an embankment here, you put a reinforcement like this, it is called basal reinforcement beneath the embankment. Then there is another case where we have seen the embankment on soft soils, like you have a prefabricated vertical drains, but then you have a reinforcement here that helps a lot in designing this whole thing. This can be even stone columns also. This can be a combination of stone columns, this can be prefabricated vertical drains. What we are exactly doing is that we are putting a reinforcement here, and to see that the loads that you are getting here are lesser than lesser, or it can be done faster and all that, that is an advantage here. Then this is another one which is called geocell embankment, which will show you some figures I will show you, where you have in a cell stone matrix is material is kept here, and that is one way of doing it along the length of the embankment. And then the other one is another interesting case, for many of the railway lines in soft soils, railway projects or highways, these things are all done. You have pile foundation, and to reduce the load on the piles, you put a reinforcement layer here. Actually, courts are available. In fact, you go to Scandinavian countries or many of the Netherlands and many other places where soft soils are in abundance, even in UK, all these techniques are used very well. If you are a geotechnical engineer, you will be very happy to deal with some of these problems, because you see these theories applied so well, and you get the benefit out of this technique. Say for example, there is one which I was directly related with one project in Berlin, where the soft soil is so poor, but then you have a high speed train going on the it's like this type of construction, in which you have a railway embankment constructed with geogrid, and then you have a combination of piles and geogrid combination. So, it was very effective, and the train speeds are not less than 150 or 100 more than kilometers per hour or something. That is very good. So, what I want to say is that this technique has lot of applications. So, this is the way that we put, like you have a geocell, as I just mentioned. This is actually a geogrid, okay, and we need high tensile geogrid to maintain the stability and prevent failure. And as the foundation shear stress increases, the required geocentric tensile force, like this is another condition, that what exactly happens is that you have shear stress induced in the embankment as well as soil, okay. So, if the foundation shear stress is higher, then there is no need to because of stiffer material or better material, then the geocentric force can come down. So, essentially what you are trying to do here is that you are trying to place this high tensile reinforcement to prevent this lateral spreading and increase confining effect and all that, okay. So, what are the mechanisms that we can see here? And we always use the established geotechnical methods in this case, and there are three mechanisms that we should address. One is called rotational stability, the second one is called lateral sliding, the third one is called bearing capacity. See, because we have placed, why is it the internal stability important? As I just mentioned, you are placing a reinforcement, and the reinforcement should not lead to any difficulty or failure. So, what is important in that case is that the embankment tries to slide, and if you have if the reinforcement can prevent it by having a good resistance at the interface, then it is fine. So, that is one failure criteria. Then the overall stability is that the slippage across the foundation can happen, like it can, I will show you that, and stability in the foundation is another issue. And then so what is this rotational stability? Like I was just trying to the example is that, say for example, this is that failure surface, right. If this is a failure surface and the driving forces are like this, and then the resisting forces are in the opposite direction. So, if this driving force, this is the embankment material, okay, and this is the reinforcement. So, when there is a tendency for the reinforcement to slide, there is a component of tensile forces that gets mobilized here, and what happens is that the direct sliding is, the rotational sliding is prevented. What happens, there is a one component of the tensile forces that interacts with this, and then it reduces the driving forces. This is the driving forces, and this component of the tension force acts in this direction. So, this is one mechanism in which it helps, and to assess this rotation stability, rotation of this material. In fact, Kandla port trust, I have seen couple of failures in which you try to stack a material, and if there is a soft soil is poor, then the whole material gets collapsed, and you only see finally a water body, because the soil is fully saturated. What we try to do is that we try to have these simple methods of analysis like Bishop's method for circular surfaces, which we know that we try to take the slices, vertical slices we divide, and then wherever there is the factor of safety is calculated considering the moments or the vertical forces and horizontal forces. That is what is done in any of the stability analysis methods. So, when you introduce a reinforcement, so for each slice, but that you have here, say for example, you have a slice here. So, you have a component of the tensile force that comes into picture that enters the stability calculations, and then that gives you the factor of safety, improved factor of safety using this geo-grid reinforcement. Okay. So, failure surfaces can be deep seated or shallow, depends on the thickness of the clay here. So, that is one way of handling the overall stability. Then what is this lateral stability sliding? As I just mentioned, the moment you address the overall stability, then you need to address this also. Like, what happens, there is you have a structure like this, and there is a tendency that this material would like to go out of this, like this is a material that it likes to come out. So, this is called the horizontal movement of the fill driven by active wedge. This is a wedge which is trying to push out of this embankment. So, what we do is that we have a reinforcement force that acts in the opposite direction, which will prevent this wedge from moving out. So, reinforcement tension develops in the plane of the reinforcement in the same section, we will see that. Okay. So, the resistance to lateral sliding is determined from the active driving force. So, the geosynthetic soil interface should be obtained from testing, that is another important factor that we should see. So, if you are able to handle this lateral sliding by considering this resistance to sliding, then it is fine. So, we know how to handle the overall stability or the global stability and lateral sliding. Now, what is this foundation extrusion? What it means is that, see, you have put a reinforcement is there, everything is fine, but then the possibility is that if the solution, if the soft soil thickness is more than the thick embankment base width, say for example, this is the, you have say for example 10 meters is the width of the embankment. Say for example, what is the typical width, maybe say for example 4 meters or something like that, and then you have a height of 4 meters, and then this is 1:1 slope, and it will be say for example, this is say 4 meters, this is 8 meters, this is 4 meters. So, totally 12 meters, and soft soil is say 15 meters. There are quite natural in some places. If this soft soil thickness is more than the embankment base width, a bearing capacity analysis is required. In some places, because it can fail by bearing capacity. Maybe it is nice that you can construct, but then the possibility is that if the whole thing sinks, it is a risky thing. So, you need to do a bearing capacity analysis, and that is the reason why you may have to even provide stone columns in some cases. Why doing so that the bearing capacity analysis shows that. The other case is that if the soft soil layer thickness is less than the embankment embankment base foundation. So, for example, instead of 12 meters now, as I said, this is 8 meters, this is 4 meters, and this is 4 meters. Instead of 12 meters now, it is less than that, maybe 6 meters. So, the possibility is that still the plastic squeezing, we call it extrusion. There is a plastic material, it just tries to come out. This whole block tries to come out of this material, it does not want to support because it is weaker. So, how do you avoid that, or how do you analyze that is something very important, right. So, this what sometimes we do is that solution for this is to reduce the settlement by making the base stiffer. We try to put some material, if it is say for example, shallow depth, maybe 2 meters or something, one can put a geocell matrix, that is what we do. Okay. Then these are all what is called ultimate limit states. Ultimate limit state means factor of safety and stability is an issue. Then you have to go for deformation. Deformation is in terms of the serviceability requirements, which is like you do not want a lot of settlements in the embankment, total settlements. So, for example, if the settlements are like this, that is maybe 100 mm, 200 mm, it is very bad. So, you want to see that settlements are minimized. That can be only possible by having a stiffer geogrids, stiffer materials. Geotextile, anything can work as a reinforcement material, but stiffness is very important. So, stiffness will lead to resistance to deformation. Higher is the stiffness, higher is the resistance to deformation. So, these aspects need to be addressed in design. Okay. So, both ultimate limit state and serviceability to be considered in the whole analysis. So, this is what I was just mentioning, that okay, if you have a reinforcement, you have to consider this do a slip circle analysis, and what happens the thing is that the stiffer reinforcements will alter the failure surface. That is what happens, because as I said, there is a component of tensile forces that comes into play here, and that will alter the failure surfaces, and it will search for a new failure surfaces. Maybe it is initially it could be like this, and the factor of safety may be 1 or 1.1 or less than 1, but the moment you put it, it shifts the reinforcement, and then there is a higher resistance mobilized and all that. And fortunately, there are many programs that are available to consider both non-circular and circular failure surfaces, okay, like based on Bishop's methods, Morgenstern-Price method and Fredland method. There are so many methods that and considering a lot of assumptions that are involved in the slices and all that, like the slice function. There are many issues there. So, one can use all those programs in an intelligent manner and then arrive at what is the tensile force required to keep this embankment stable. That is a point here. Another point that I would like to highlight to you is that when there is a soft soil, how does the shear strength vary with depth? Actually, if the soft soil is too shallow, one can assume uniform variation of underlying shear strength with depth. Like you do a CPT, cone penetration test, and if it shows a vertical line roughly varying along a mean value, then you can take that the variation of shear strength with depth is constant, and that is applicable in soils of limited depth. But there are some cases where the strength increases with depth. Again, one can get the information from cone penetration test, and if the soft soil extends to deeper depths, you better consider that whatever is there, because of the with the increase in depth, always shear strength increases, right. With increase in, say for example, the when shear strength value will be higher at a deeper depth than when you have a sample at a shallow depth. So, that information is quite important, because when you try to do the analysis, should I do that it is just based on limited depth or it is unlimited depth is also useful, because it will as I said, the failure surfaces, right, the failure surfaces they keep on searching, and if you make since here the depth is higher with the depth there is a shear strength increase, it will have a higher factor of safety than considering this. Like you take a case where the shear strength is uniform for 5 meters, and you take the same thing, shear strength is increasing with depth. The case with which the shear strength increases with depth, it gives a higher factor of safety than this former case in which the shear strength is assumed as constant. Why? Because we know that there is an additional component of strength that comes into picture, and we know that the strength of the soil is non-linear, that factor is taken care and all that. Okay. So, how do you make all these calculations? So, if you are looking at this is the actually example. So, the thing is that you have vertical loading from the embankment is there. This is how the outward shear stresses develop. Okay. This is how the outward shear stresses develop, and you have the the earth pressure from the fill. Okay. So, that fill is that horizontal outward shear stress. This is a shearing, shearing is taking place if you just keep on constructing, that is because of the vertical loading. Now, you put a reinforcement, what is happening because of this reinforcement, there is an opposite force that you have introduced, what is called inward shear stresses. You have introduced inward shear stresses. There is an outward shear stress, and there is now that you are trying to nullify by using some inward shear stresses. Okay. So, if you want to analyze that, you have to see this. So, what is the vertical load that you have, and what is the outward shear stress that is coming from this fill. So, to prevent the lateral spreading of the embankment, the horizontal stresses within the fill must be balanced by shear reactions at the base. So, in an unreinforced embankment, the lateral thrust pre-fill in the is transferred to the foundation, right. Whereas, if the reinforcement is present, some of the thrust is carried by the reinforcement itself. So, that is a nice thing, like so you are trying to balance the outward shear stresses and the inward shear stresses, and what is happening there, it is because of the main factor that contributes to this is that the moment you include a reinforcement, it allows a preferential direct sliding occurring at the surface of the reinforcement layer, and slippage occurs if the available reinforcement at the resistance, there is a resistance like shear resistance which you have introduced. See, there are shear resistance, actually there is a clay is there, then there is a sand or embankment material. So, if you place this reinforcement at the interface, okay, at the interface you have to normally place at the interface. So, you have a resistance here which is nothing but, like, you can calculate like this, the direct sliding force at the interface is nothing but, it is given in terms of the alpha. We have seen in the GeoGrid's calculations that the coefficient of direct sliding one can calculate. It's it's nothing but the variation of shear stress as a function of normal stress. Okay. So, that coefficient is a normalized ratio, right. So, that you will get, and one another important thing is that I am trying to express that in terms of NH. If n is the slope of this h is the height of the embankment, I said 4 meters. So, if I want to express it is to 1 is to 2, I should say n equal to 2. So, n becomes 2. So, it will be 2h will be the horizontal slope. So, this is 1, this is 2. So, this n is also important. So, what I am trying to do is that I will try to calculate gamma is the weight, nh is the horizontal force, height is the vertical. So, gamma h square by 2 into n, vertical and horizontal both will come into picture, and then this is the vertical force acting, and I am trying to convert into direct sliding force. So, this is a factor that we know we have to use, and this is one thing, right. So, this is actually the resistance available, okay. And what is the active force? This is actually the resistance that you have from this fill, and the active force is nothing but gamma h square by 2 plus QH. QH is from the surcharge, Ka is the earth pressure. So, yeah, alpha ds tan phi d, and this is that P fill, and you have to equate both of them, right. So, once you equate it, you get a factor which is n, you just equate both of them and simplify this, and then what is that n you have to minimum you have to k, this is k is nothing but 1 minus sin phi by 1 plus sin phi, right. Like we know the embankment material properties, like say assume we are using a sand. So, you can use 1 minus sin phi by 1 plus sin phi. So, then q is a surcharge and everything is known. So, n what should be, n should be minimum, you will get what is the n value you should provide, one can get, okay. That is one thing, like what is the n value. If you make it very steep, then it is going to fail, but what is the n value minimum you will get from that. So, that you can design based on this alpha ds factor, okay. Alpha maybe say for example 0.8, it could be 0.6. That is other one. One more thing is that slippage across the foundation surface, in fact it should not see, as I said, it should not slip through the reinforcement, and then it should not also slip through the soft soil. So, we have used a factor alpha ds when it is trying to slip through across the reinforcement, but when you want to say across the foundation surface, foundation has what is called the shear strength of SUD, okay. That actually again here what we do is that, yeah, this is the slippage across the foundation, right. So, we say shear strength of the soil into NH will be the resisting forces, and the active force is this, which is nothing but you calculated from gamma h square by 2 into Ka into that surcharge and all that. So, you just equate that thing, and then you get an n value. It is simple that the resistance series just n SUDH, you are trying to equate it to this, that is it. So, you get another one more n value, whichever is higher you take it, okay, whichever higher you take it, and so that way you have got the n value which is required to see that it does not fail across the reinforcement or through the clay layer, both n values you could get, that is very useful. but then you should go further. Then what is that that I was mentioning about the found extrusion, right? See, vertical stress causes an vertical stress in the foundation soil and a corresponding increase in the horizontal stress. The lateral stress developed eventually causes the foundation soil to get displaced laterally beneath the embankment side slope. Why is it? It is just leaving. It is because the vertical stresses are going to be high, and then they become horizontal stresses, and then it tries to go out of the direct loading. So, it does not want to take load, that is what is happening. So, how do you analyze that? It is just like this, you take a vertical stress which acts uniformly, and what happens is that the block that we have here, you can see the block here. So, if it is of limited depth, you have vertical stress acting, and then there is also alpha SUD is another coefficient that you have, some portion, because shear strength is there here acting, the Venn shear test, you can get a Venn shear test value, you can get the Venn test value, and sigma V minus 2 SUD is the thing is that vertical stress is see, there are two surfaces here, one is this SUD is acting here, SUD is also acting here, right. So, you can say that it is the two surfaces acting, and the other possibility that we have is that you take this as alpha is equal to 1, okay. When alpha is equal to 1, it becomes 2 SUD, okay. This side 1 and this side 1, and then when you come here, see what is the vertical stress, see the thing is it becomes vertical stress is sigma V here, vertical stress in this soft soil, this sigma V, and this total stress is so much, and sigma V minus 2 SUD, because you have to say that the shear strength is reducing that much. So, once you, so this is somewhat lesser value here, then as you come here it is higher, I mean in the sense 2S, this is a horizontal forces on either side, and why this is happening is that it is because of the principal stress rotation, okay. What is that principal stress rotation? Under that load it is sigma V minus 2 SUD, but then once you come here, it is like you take an element next to the load, and then the other one just next to that, whatever is a major stress here, and then there is a minor stress here, for this element it becomes a major stress here for the just above this thing. So, we call it a principal stress rotation, and that can be this understanding can be used to calculate what is called like this. Say for the case where there are no outward and shear stresses, we can say that the alpha is 0. There is one case that it is just under equilibrium, and the lateral sliding of the soil block is resisted by the available shear strength of the horizontal plane. So, that is nothing but N SCD into H, very thickness of this soft soil, it is actually the height of the embankment, okay. So, NSCD is nothing but this is one equation equal to 2 sigma V minus 2 SUD into D minus 2 SUD, this is that you should use, and once you simplify that you will get a term called N based on these considerations, again one more N, which is nothing but which prevents you to reduce the the plastic squeezing, okay. So, this is another term that is a simple direct equation that you get from here. Let me just elaborate it again here. Okay, this is a simple equation that you get here, which is nothing but by considering this when the outward shear stresses are equal to inward shear stresses, then alpha is 0. Like I'll just show you some more examples here, and yeah, this is a variation of shear stress with depth, this is the variation of shear strain with depth, this is the variation of displacement with depth. And see, the thing is that when see, this is assume that this is a rigid foundation which is available at some depth d, right, this is a d. So, what the shear strains are, as we just there, the displacement is maximum here, and it is like it depends on the how much of inward shear stresses and outward shear stresses have balanced. Okay. If the thing is that if the shear stresses are not, see, the thing is that if outward shear stresses are something and inward shear stresses are they are equal, then still there will be some settlements. But if the inward shear stresses are going to be much more than the outward shear stresses, then the displacements are less. So, if the inward shear stress and outward shear stress are equal, then you still have some settlements, that is just because of the equilibrium conditions, you will get some displacements. But if the inward shear stresses are going to be higher, then definitely you will have stiffer lesser displacements, and that is how these two also come into picture. Like the resistance in the foundation is just, that is what will as a function of shear strength is like this, when the outward shear stress is equal to inward shear stresses. But if the inward shear stresses are going to be higher, then it will come down. So, if you can design a proper reinforcement such that you will have a very good inward shear stress resistance, then it is going to be excellent. That is what we did, when there are no outward or inward shear stresses acting on this tip of the soil block, this is what we say, and we write a simple equilibrium condition. So, we get some n equation for n. So, that is one thing. So, it is all direct simple mechanics. And how do you calculate the deformation in the foundation? Like, the thing is that when you apply load, how much of shear strain it comes? Actually, this comes from, the shear stress D is the, as I just mentioned, D is the depth of the soft soil. Maximum shear strain is you put in terms of the gamma max, and we assume a distribution like this, because at the rigid boundary it is 0, at the top it is maximum. So, it is by 2 we use, and the shear, it is nothing, shear strain is nothing but shear stress divided by the shear modulus, right, maximum shear stress induced divided by shear modulus. So, you are able to get even how much of lateral displacement is taking place. And what is that maximum shear stress? Maximum shear stress is nothing but the shear strength of the soil, where it is a straightforward equation. So, you are able to even get how much of lateral displacement is there, one can get here. So, that we will all calculate, and why is it? So, our objective is to see that this is reduced and to the minimum. So, how is that reinforcement is helping here? As I just mentioned, the mobilization of shear stress at the interface is an important factor in the efficiency of the reinforced embankments. The shear stress could mobilize inward, outward, or become nil depending on the extensibility of the reinforcement, shear strength of the soil, and the loading conditions. What happens? The three conditions, like if there are only outward shear stresses, you have the it's -1. If the inward shear stresses are equal to outward shear stresses, they are 0. Then there is a full inward shear stresses, it is called it is an excellent condition that we want. So, based on that, actually we are using that factor what is called alpha here, just to see, I said inward and shear stresses that equal, then you try to calculate the block equilibrium and then equate it to what is the n required, that is what we have seen. On the same logic, you can even calculate the height of the embankment, that which is in fact, so if alpha is 0, the inward shear stresses are equal to outward shear stresses, but if alpha is going to be quite substantial, then it comes into picture. This is again a simple equilibrium equation that one can derive, and so the following relationships hold good for the embankment on the foundation of uniform under shear strength SUD and limited depth D. All these equations that I am going to present now are valid for cases where the depth of the soft soil is limited. Say for example, maybe 5 meters is the height and 4 meters is the thickness of the soft soil. So, something like that. So, we actually, as I just mentioned earlier also, that it can be even different, like it can be shear strength can increase with depth also, but then I am not giving those equations. And actually this is a work that is presented by Jewell, Jewell, who wrote a very good book on embankments on soft soils. There is a very good chapter in his book, and there are a number of papers in geotextiles and geomembranes. He gives lot of information on derivation of these equations, their applicability, case studies and all that. So, from that literature I have taken these equations, where they are valid for just the depth of the soft soil is limited and you have an embankment construction. So, say for example, you are trying to construct a 4-meter high embankment, soft soil depth is 4 meters, how do you handle this? And if you want to have more details, one can see those papers in geotextiles and geomembranes. So, the embankment height is known, like h equal to 4 meters, 4d, as one can derive this equation. And then the factor of safety of the reinforcement is also one can do, like it is simple, that it is a simple equilibrium equation, and these equations one should remember to solve some of these problems here. Like it is again higher is the embankment factor of safety can be calculated using this simple expression. It is nothing but the driving forces to resisting forces, nothing else, it is just a horizontal equilibrium. And what is the displacement also we have seen, it is simply that I just mentioned SU d by 2g, we have already seen that. But how is that alpha is coming into picture? Alpha is that when inward shear stress equal to outward shear stress, alpha is 0, and if you have alpha term, how does it influence? Because alpha is another important variable, and that what we see, that is one term. The other important thing that is that how do you calculate the reinforcement force? You also have a simple equation that one can derive, that is nothing but PR, P is nothing but it is in terms of this again all these parameters, gamma h square into alpha n d divided by 4d plus all these terms will come. And in the case of unreinforced embankment, the factor of safety reduces to, in the previously I have shown you the factor of safety for reinforced embankment, the factor of safety reduces to this. So, you have all the equations to solve this particular issue, and say that is for the case of an embankment which is resting on a soft soil of limited depth. One can even go for other case where the embankment is resting on soft soil of unlimited depth, that equations are also available in literature. I will just try to use these equations to illustrate their applicability. It is just the principle is illustrated here. You have a 200 meters length of the embankment, just a small approach road between two places maybe, and height of the embankment is about 4 meters. And the width of the crest is 15 meters, like 15 meters is the width of the road, and the soft soil is about 4 meters depth, and the shear strength I know 15 kN per meter square, and it is constant with depth. The embankment is to be constructed rapidly in one stage, and end of construction stability needs to be ensured. So, we need to calculate what is this the factor of safety with reinforcement, without reinforcement. You should be able to select a reinforcement force which will give you reasonably safe factors, as well as like factor of safety I said target factor of safety is 1.3, right. So, here the embankment needs to be constructed at one stage. It is very clear that I can't construct at 1 meter, 2 meters, then wait for 2 months and then again construct 2 meters. I would like to construct all the embankment needs to be finished in one go. With I put a reinforcement, then start going, I want faster, that is objective. I showed you the diagram in which the factor of safety at the end of the construction is the minimum actually, because so we have to see that end of construction stability needs to be ensured, that is there. Okay. So, for that step 1, like the factor of safety of 1, factor of safety using this reinforcement is this equation. Sometimes though I have in the problem we know that it is 4 meters is the height of the embankment, you can even take 4.5 in calculations to be on the safe side. Okay. That is one thing. So, the target factor of safety is 1.3, SU is given 15, gamma is known, height is 4.5 I am taking, alpha plus this is the equation that we have, and if you simplify, if alpha equal to 0, as I said, n value little steeper, but if the thing is that alpha value, like if you want high full invert shear stresses, right, this is so is excellent, reinforcement is very effective, right. Full invert stresses, the n is 1.69 only. You can see that you are able to number one construct with for the target factor of safety of 1.3 here, n value can be 3.38 if you take a lower geograde quality, or if you take a somewhat where the invert shear stresses are going to be higher, this n is 2.25, and if you take a very good geograde material or geotextile material, it is 1.69. So, what you have done here is that you are able to normally, like I will show you that without factor of safety what happens, like if without reinforcement what happens, you can use again the similar expression that I have given for all these n values that we have got, like I got 3.38, 2.25 and 1.69 for different values of alpha, which characterize the relationship between the inward and outward shear stresses. And for the same n values, you can see that the factor of safety is it is 0.84 here and 0.94 here, 1.12. So, under no conditions I can get without reinforcement, I can't get a factor of safety of 1.3 without. So, with reinforcement only I am getting I got a factor, this is a expression for without reinforcement. So, with reinforcement I am getting a factor of safety of 1.3 because I have used it in the equation, and with if higher is the stiffness, higher is the n lower is the n value. Okay. So, normally you can see that if this is a without reinforcement actually, as we know that if the embankment is steep, the factor of safety is less, and so it is 2.25 means it is much more flatter, point factor of safety 1.94, and 3.38 it is flatter and 1.12. What is the difference between all these three things is that the area of cross section, see the thing is that area of cross section of the sand embankment material required. If I go for a very stiff geograde, I can only go for 1.69, and the area of cross section that is required is reduced, like say for example, it is meeting a target factor of safety of 1.3, and at the same height, if 4 is the height of the embankment height, 1.69 into 4 will be the horizontal width, the width in the this thing. So, otherwise it is 3.38 where you need large quantities of sand or embankment material, which is going to be quite expensive, right, in a place like soft soil where exists in say Kerala or Andhra or any other place, like say for example Kakinada or Paradeep or any of the soft soil areas. So, this is a very important thing that one can understand, that if higher is the thickness of the stiffness of the reinforcement, better is the savings achieved, and also you will get a good factor of safety which is targeted. Okay. Okay, this is unreinforced. Now, how do you get reinforcement force? Now, I know that yes, there is a, if higher is the stiffness, it is fine, but how do you calculate the reinforcement force? So, this is an equilibrium equation that we have given earlier, and you substitute all the quantities required, and you will get a geograde strength 157, say in this case 117 or 118 kilonewton per meter for alpha equal to 0.5, and if I am just going for simple alpha less than close to 0 where inward shears are equal to outward shear stresses, you do not need to go for high quality geograde. Actually 60 kilonewton per meter, it is also it is expensive compared to in certain conditions, So, 60 kilonewton per meter is one thing, and you can see this is almost double. Of course, this has to do directly with this, and you can see that this is the end of the at the design strength of the geograde. Okay. And now, what is its stiffness? Stiffness is, you have to calculate the stiffness also, because manufacturing companies will give you the geograde tensile strength, stiffness, properties, all the properties are given. As I said, stiffness is also very important quantity to reduce the settlement. So, what is the J, we use a term. So, actually allowing the 10% is allowable strain, shear strain required, like assuming strain compatibility that we discussed earlier, like P required divided by P allowable will give you that in fact it is 0.1. So, it comes to about 1180, this 117.978 by 0.1 actually. Okay. So, which means it comes to roughly 180 and then here 595. So, 600 kilonewtons per meter length will be the stiffness of the geogrid, and this is the force. So, how does it really matter in terms of the displacement? So, in order to mobilize design shear resistance SUD, some shearing strains is nearly is required, which is actually why I just what is the basis of this 10%, like you see you do what is that Vane shear test, right. Vane shear test, if you do it, just you do the Vane shear testing, it gives some number which is an ultimate shear strength. Actually, you take the same sample in the lab and then conduct a stress strain curve, that will be roughly about 9 to 10%. Large strains only it is mobilized, because the soil is normally consolidated, most of the soft soils are normally consolidated and the strains are much higher, and we assume that at 10% of the strain level, the strain gets mobilized. So, we use a term, and now that is why I said 10%. The shear modulus is given by, we know that this is a term, and delta H is a horizontal displacement. So, if you use this expression, how do you get? In fact, you can see that for a stiffer grade of the reinforcement, horizontal displacement, how much it moves is 100 mm and it is 200 mm in the other case. So, this shows that high reinforcement force will reduce the lateral displacement, that is very important. Now we know how much is the reinforcement force required, and you know how much is the stiffness required. You have some rough idea of what is the influence of this alpha factor also, and all that factor of safety, everything is fine. Now you have to choose a geogrid, and the information is that geosynthetics are available with index strength in the range of 200 to 400 kilonewton per meter. Okay. One company, the different companies have, and how do you choose that based on this? So, the index strength is to be corrected for loading period, which is equal to 90% of the consolidation, okay, and for temperature corresponding to ground conditions, assume that it is temperature 20 degrees, and under these conditions the manufacturing data shows that at the end of 90% consolidation, time equal to 2.5 years, the reference strength is 60% of the design strength. Okay. So, why is that 90%? The consolidation has to take place and the reinforcement has to be there, right. Reinforcement has to be effective till in all its complete process, right. So, we take it as 90%, and it is for 90% of that it takes for the soil, clay soil, it is 2.5 years, right. So, for 2.5 years, the reference strength of the geogrid, it is 60% of the design strength. Whatever is that earlier we have chosen, that should be reduced by this number, and allowance for even this damage and has to be done, environmental conditions are to be done. So, if you do all that, you take an index strength of about 200, what happens? So, reference strength is 0.6 into 200, it is also 120, and then the field strength values again 120 divided by 1.2 into 1.1, so 91. Design strength is again you need to have another factor of safety of 1.3 global. So, 91 divided by 1.3 is 70. So, the stiffness is 70 divided by 0.1, shear strain is 700 kilonewton per meter. So, if you take this 200, it will serve this purpose, right. So, and if you take 0.5 case, it is again you can choose another one, like instead of 200 you can take 400 one. So, what I want to say is that see this in the previous case we have calculated the other one also. So, you based on these two things, the reinforcement function, see the thing is that if you want to both this whatever 200 to 400 kilonewtons or whatever, one can make a choice, appropriate choice of the geogrid materials, right. Like as I just mentioned, so here the construction sequence is quite simple, where you just do that clear the ground, put the geosynthetic material, then start putting the embankment construction. Even it can be in layers also. Normally, we assume that, do you remember that we just assumed only one layer, the interface shear resistance is going to be, say for example, you take, it can be measured in the laboratory also. You have to do a direct shear test to do that alpha factor, and all can be calculated. So, it is this example clearly shows that one can design the reinforcement one can design the reinforcement function for an embankment and a soft soil, and one can arrive at suitable quantities of the whatever properties and the all other issues that are related with this, like stiffness, then the other factor what is called the design strength, stiffness, and the alpha ds. There are three factors that are important from the foundation design in this case. And with this I will conclude. Actually, I want to tell you that there is one geotextile embankment also we have done in long back when I was in Central Road Research Institute. We installed a particular case in one place where the soil is so soft in the it is like a paddy area, and an embankment was constructed in this paddy area, which is something very soft actually. So, the geotextile layer was put, and then after an embankment was constructed, and it was put to use immediately. Earlier it was not possible at all. So, with this I will conclude, and we will see some more aspects of the same thing, like use of geocells and what are the other applications and case studies in the next lecture. Thank you.